Hi, I'm Sean Hillers, and this is my Physics 1 Lab 5 on planetary motion, which I'm doing again, but sort of with a little twist. So this is the introduction. Sort of the purpose of this lab was to model and understand celestial motion if the larger body isn't fixed in space. We're looking at a bunch of celestial bodies, and the larger object, usually the sun or the black hole, was fixed in space. But I wanted to see what would happen if both of them were moving at the same time. So some of the models and principles include Newton's second law, gravitational potential energy, and the conservation of energy. And there's a preview of a picture from the code. And you can see both objects orbiting each other. So here are some equations that I used. Newton's second law to see the forces. And then there's also the force of gravity, which is also the main force being used here by the planets, causing them to accelerate. And then there's the velocity update equation, which is used to see the velocity at different times in the code. And something very similar can be said about the position update equation, which is used to see the update in position. So the model and assumptions used Web v Python to perform the calculations, and I assumed that these two bodies were the only bodies imposing any force in the system, and that nothing else was happening around them, as well as the fact that the bodies are perfectly round, so that the mass is equally distributed, and there's no extra difficult calculations that we don't really know how to do. So for the system and surroundings, the system would be the smaller star, and the surroundings would be the larger star, which is imposing the forces. Conditions, I started with the base code from Lab 3, just to change it a bit for both the objects to move. And then it had a random starting velocity based off like the name you put into, and both stars start with the starting velocity. And then so the whole thing after that is I'll get into about finding the mass for the two stars and define the starting velocities that work. As for the details experiment, the initial velocity we start with was unknown, and we had to input two different masses that would allow for a stable orbit. The two masses worked well were 5.25 e to the 40 and 2.5 e to the 40 for the larger and smaller one. And this is probably not the only one, but this is one of the ones I found that worked pretty well. For the code, I changed it to of course, I changed it to a stop in the second part of Lab 3, like if the rocket crashed into the moon, or yeah, then it would stop the whole thing, so that I could just keep inputting masses until the whole system worked. And then as for similarities and differences, compared it to real life binary star system, and it's similar in most cases that one star is much larger than the other in order to keep the balance, which is something I had in mind as well. And the velocities are probably much different, than in real life, which can just the difference in masses. The masses I used were incredibly large, much larger than most stars. For sources of error, there were a bunch of approximations, such as no outside forces, and some other things to make it just easier to run the simulation, and then also use trial and error to figure out the two masses. There's definitely a more optimal solution, but that's just definitely wasn't in the scope of this lab. And as for additional questions, the third star was added to the mix, called a three-body problem, and is widely discussed. People are trying to solve. Some orientations have been solved, but most have not been. And as for what could happen, depends on the starting velocity and where it is, where the other two are, and just in general, a lot depend on it. And as for if planets were added to the system, would it be able to orbit like a singular star system? It is possible, and there are two types of orbits. It could either be one star or both stars, but it would be quite hard to accomplish. And thank you for listening.